When dealing with stationary motors, correctly sizing the branch circuit protective device is crucial for safety and code compliance. The motor itself can act as a controller in some cases, and you need to determine the largest allowable protective device. The determination largely depends on the motor's horsepower. For a motor rated at 1/2 horsepower, the maximum size of the branch circuit overcurrent protective device is specifically dictated by the National Electrical Code, or NEC. The NEC contains tables that provide guidance on sizing overcurrent protection for various motor types and horsepower ratings. To find the precise value, you need to consult the applicable NEC table, typically found in Article 430, which deals with motors, motor circuits, and controllers. The relevant table will list the maximum percentage of the motor's full load current that the overcurrent device can be rated at. This percentage varies depending on the type of overcurrent device, whether it's an inverse time circuit breaker or a fuse. For instance, the NEC might specify that the overcurrent device can be rated at no more than 250% of the motor's full load current when using an inverse time circuit breaker, or perhaps 175% when using certain types of fuses. To use the table, you first need to determine the motor's full load current, or FLA. This information is found on the motor's nameplate. The nameplate will list the current the motor draws at its rated horsepower and voltage. Once you have the FLA, you multiply it by the percentage given in the NEC table to determine the maximum allowable rating of the overcurrent device. It's important to note that this calculation yields the maximum size. You can use a smaller overcurrent device if needed, but you cannot exceed the maximum calculated value. Using an overcurrent device that is too large can prevent it from properly protecting the motor and circuit from overloads and short circuits. This can lead to equipment damage, fire hazards, and potential electrical shock. Conversely, using an overcurrent device that is too small can cause nuisance tripping, where the device trips unnecessarily due to normal inrush currents when the motor starts. The NEC allows for some adjustment in the size of the overcurrent device to accommodate motor starting currents, but this adjustment is limited to prevent oversizing. If the calculated value for the overcurrent device is not a standard size, you are permitted to round up to the next standard size, but only to the extent allowed by the NEC. The NEC provides specific rules for rounding up to prevent excessive oversizing. It's also important to consider the type of motor when selecting the overcurrent device. Different motor types, such as single-phase, three-phase, and direct current motors, have different starting current characteristics which affect the sizing of the overcurrent protection. The NEC tables provide separate values for different motor types. In addition to the branch circuit overcurrent device, you also need to consider the motor's overload protection. Overload protection is designed to protect the motor from overheating due to prolonged overloads. Overload protection is typically provided by a separate device, such as a thermal overload relay, but it can also be integrated into the motor starter. The size of the overload protection is based on the motor's full load current and the motor's service factor. The service factor is a multiplier that indicates how much the motor can be overloaded for short periods without overheating. The NEC provides specific rules for sizing overload protection based on the motor's service factor and full load current. It's crucial to follow the NEC guidelines carefully to ensure that the motor is properly protected from both overloads and short circuits. Remember that electrical codes and regulations can vary depending on your location, so it's always a good idea to consult with a qualified electrician or electrical inspector to ensure that your installation complies with all applicable requirements. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult the NEC and local codes for specific requirements. The NEC provides detailed information on motor circuit protection, including specific tables for different motor types, horsepower ratings, and overcurrent device types. It also covers requirements for motor controllers, disconnecting means, and grounding. Understanding these requirements is essential for ensuring the safety and reliability of motor installations. Firstly, always refer to the motor nameplate for accurate information about the motor's voltage, full load current, and service factor. Secondly, consult the NEC tables to determine the maximum allowable size of the branch circuit overcurrent device. Thirdly, consider the type of overcurrent device, whether it's an inverse timed circuit breaker or a fuse, and use the appropriate percentage from the NEC table. Fourthly, calculate the maximum allowable rating of the overcurrent device by multiplying the motor's full load current by the percentage from the NEC table. Fifthly, if the calculated value is not a standard size, round up to the next standard size, but only to the extent allowed by the NEC. Sixthly, ensure that the overcurrent device is properly labeled and identified. Seventhly, verify that the overcurrent device is properly installed and maintained. Eighthly, periodically inspect the overcurrent device to ensure that it is functioning properly. Ninthly, if the overcurrent device trips frequently, investigate the cause of the tripping and take corrective action. Tenthly, consult with a qualified electrician or electrical inspector if you have any questions or concerns about motor circuit protection. Correctly sizing the motor branch circuit protective device is not just a matter of code compliance, it's a matter of safety. A properly sized overcurrent device can protect the motor, the circuit, and the people who use the equipment from potential hazards. Therefore, it's important to take the time to understand the NEC requirements and to follow them carefully. When selecting an overcurrent device for a motor circuit, it's also important to consider the interrupting rating of the device. The interrupting rating is the maximum amount of fault current that the device can safely interrupt. The interrupting rating must be greater than the available fault current at the point of installation. Available fault current is the amount of current that would flow in the event of a short circuit. It depends on the impedance of the power source and the impedance of the circuit conductors. If the interrupting rating of the overcurrent device is less than the available fault current, the device may fail to interrupt the fault current, which can lead to equipment damage, fire hazards, and potential electrical shock. Therefore, it's crucial to calculate the available fault current and to select an overcurrent device with an interrupting rating that is greater than the calculated value. The NEC provides guidelines for calculating available fault current and for selecting overcurrent devices with appropriate interrupting ratings. It's also important to consider the voltage rating of the overcurrent device. The voltage rating must be equal to or greater than the voltage of the circuit. Using an overcurrent device with a voltage rating that is too low can lead to premature failure and potential safety hazards. Therefore, it's crucial to select an overcurrent device with a voltage rating that is appropriate for the circuit. In addition to the branch circuit overcurrent device and the motor overload protection, it's also important to provide a disconnecting means for the motor circuit. The disconnecting means is a device that can be used to disconnect the motor from the power supply for maintenance or repair. The disconnecting means must be readily accessible and must be capable of being locked in the open position. The NEC provides specific requirements for disconnecting means for motor circuits. These requirements cover the location, type, and rating of the disconnecting means. It's crucial to follow these requirements to ensure the safety of personnel who may be working on the motor circuit. Grounding is another important aspect of motor circuit protection. Grounding provides a low impedance path for fault current to return to the source, which helps to protect people from electrical shock. The NEC provides specific requirements for grounding motor circuits. These requirements cover the size and type of grounding conductors, as well as the methods for connecting the grounding conductors to the equipment and the building grounding system. It's crucial to follow these requirements to ensure that the motor circuit is properly grounded and that people are protected from electrical shock. Regular maintenance and inspection are also essential for ensuring the continued safety and reliability of motor circuits. Overcurrent devices, overload protection, disconnecting means, and grounding connections should be periodically inspected to ensure that they are in good working condition. Any damaged or worn components should be replaced immediately. Motor circuits should also be tested periodically to ensure that they are properly grounded and that the overcurrent protection is functioning correctly. These tests can help to identify potential problems before they lead to equipment damage or safety hazards. When working on motor circuits, it's important to follow all applicable safety precautions. Always disconnect the power supply before working on any electrical equipment. Use appropriate personal protective equipment, such as gloves and safety glasses. Follow lockout/tagout procedures to prevent accidental energization of the circuit. Work in a well-lit and dry environment. If you are not qualified to work on electrical equipment, hire a qualified electrician to perform the work. Working on motor circuits can be dangerous, so it's important to take all necessary precautions to protect yourself and others from potential hazards. The NEC is a comprehensive document that covers all aspects of electrical installations, including motor circuits. It's important to have a copy of the NEC and to be familiar with its requirements. The NEC is updated every 3 years, so it's important to have the latest edition. You can purchase a copy of the NEC from the National Fire Protection Association, or NFPA. The NFPA also offers training courses on the NEC. Taking a training course can help you to better understand the NEC requirements and to apply them correctly. In addition to the NEC, there may also be local codes and regulations that apply to motor circuits in your area. It's important to be familiar with these local requirements as well. You can contact your local building department or electrical inspector to find out about local codes and regulations. Complying with the NEC and local codes is essential for ensuring the safety and reliability of motor circuits. Failure to comply with these requirements can lead to fines, penalties, and potential liability in the event of an accident. Therefore, it's important to take the time to understand the applicable requirements and to follow them carefully. Motor control centers, or MCCs, are commonly used to house motor starters, overcurrent protection, and other control equipment. MCC provide a convenient and organized way to manage motor circuits. MCC are available in a variety of sizes and configurations to meet different application requirements. When selecting an MCC, it's important to consider the number of motors that need to be controlled, the horsepower ratings of the motors, and the available space. MCC must be installed and maintained in accordance with the NEC and the manufacturer's instructions. Variable frequency drives, or VFDs, are used to control the speed of AC motors. VFD can save energy by reducing the speed of the motor when it's not needed to run at full speed. VFD also provides smooth starting and stopping of motors, which can reduce wear and tear on the equipment. VFD must be installed and maintained in accordance with the NEC and the manufacturer's instructions. When using VFD, it's important to consider the potential for harmonic distortion. Harmonic distortion is caused by the nonlinear characteristics of the VFD power electronic components. Harmonic distortion can cause problems with other electrical equipment, such as overheating of transformers and neutral conductors. The NEC provides guidelines for mitigating harmonic distortion caused by VFD. Surge protection is also important for motor circuits. Surges can damage motor windings and other electrical equipment. Surge protection devices, or SPDs, are designed to protect equipment from surges. SPD should be installed at the service entrance and at the motor control center. The NEC provides guidelines for selecting and installing SPD. Power quality is another important consideration for motor circuits. Poor power quality can cause motors to overheat and fail prematurely. Power quality problems can include voltage sags, voltage swells, and harmonic distortion. Power quality monitoring equipment can be used to identify power quality problems. Once the problems have been identified, corrective action can be taken to improve power quality. Energy efficiency is an increasingly important consideration for motor circuits. Energy-efficient motors can save significant amounts of energy over their lifetime. The NEC provides guidelines for selecting energy-efficient motors. It's also important to properly size the motor for the application. An oversized motor will waste energy, while an undersized motor will overheat and fail prematurely. Proper maintenance and lubrication are also essential for maximizing the energy efficiency of motors. By following these guidelines, you can ensure that your motor circuits are safe, reliable, and energy efficient. And remember, always abide by local codes and NEC standards for proper and safe sizing of electrical equipment.